Will this airplane fly? If we take a very weak X-ray, how can we create an image of the interior of the human body using that X-ray? What if we want to design a bicycle frame that has both a low weight and a rigid frame? How much would the average temperature of the Earth increase if the amount of carbon dioxide in the atmosphere increased by 20%? We can get at answers to these questions through modeling with differential equations. Differential equations are among the most powerful tools we have for analyzing the world mathematically. Okay, some other applications include modeling the spread of disease, weather and climate prediction, traffic flow, financial markets, population growth, water pollution, chemical reactions, suspension bridges, brain function, rockets, tumor growth, radioactive decay, airflow across a wind plane, electrical decay, planetary motion, vibration of guitar strings, predator and prey models, and a whole host of other things. So differential equations are an incredible tool that we have in mathematics. So what is a differential equation? A differential equation is any equation that involves at least one derivative. Okay, and that can be a first derivative or a higher order derivative. So I have some examples here. So here we have y prime cubed is equal to x, y prime is equal to y prime is equal to 2xy, dp dt is equal to k over root p, y double prime is equal to negative y, and there's so many more. Okay, so there's just an incredible field of differential equations. So let's look at ways that we classify our differential equations. The first is by type. So we have two types. We have ordinary differential equations and partial differential equations. We call these ODEs and PDEs. So an ODE involves a single independent variable. Okay, so if you think about when we graph on an XY axis, okay, that x is our independent variable and the y is our dependent variable. So this dy dx, here is our dependent variable. There's our independent variable. Okay, and here I have just this one independent variable here. So this is going to be an ODE. It has one independent variable. PDE has two or more independent variables. Okay, so if we look at this example, this is the second derivative of u with respect to x. So the independent variable here is x. This one is the second derivative of u, but this is with respect to y. So the independent variable here is y. So I have two different independent variables. I have x and I have y. So that makes this a PDE. All right, so go ahead and pause the video. I bet you can figure out what these four are pretty quickly. And we'll come back and do those. All right, so number 3, I have an independent variable of y, an independent variable of x, so two different independent variables. This is a PDE. Okay, here I have the second derivative and my independent variable is x. Here I have a first derivative, my independent variable is also x. So this is going to be an ODE. Here I have a derivative, second derivative with an independent variable of x, a second derivative with an independent variable of t, and a first derivative with an independent variable of t. So I have two different independent variables here, an x and a t. So this is a PDE. And on this one, I have an independent variable of t and another independent variable of t for my derivatives. So this is an ODE. So that's one way we classify our differential equations is by type, ODE or PDE. Another way we can classify these is by order. So the order is the highest derivative in the equation. Okay, and let's take a look at this example here. So this is the second derivative of y with respect to x. So this is second order. Then let's take a look at this piece here. So this is derivative of y with respect to x. And this is the first derivative cubed. So don't be fooled by this, this 3 that we're raising this to on the outside. This is still just the first derivative. So this is first order here. Okay, and then this is not a derivative, and this is not a derivative here. So those are not relevant to figuring out the order, since the order is only related to the derivatives. We're looking for the highest order derivative. So that would be a second order. So this is a second order differential equation. All right, so let's take a look at this. So I have a second order derivative here and a first order derivative here. So that makes this a second order. Why don't you see if you can figure out what these two are? If you want to pause the video for a sec, you can. All right, so let's take a look at this. So I have an x squared here. That doesn't have anything to do with anything, but I have a y prime, so I have a first derivative. E to the xy, there's no derivatives in this piece, and the 4 definitely isn't a derivative. So all I have is this first derivative here, so this is a first order. Now let's look at number 9. So I have an x that's not a derivative, but this y prime is a derivative. It's raised to the 4th power, but that doesn't matter about anything. So I have a first derivative here. I have a y, that's not a derivative, and I have an x, and that's also not a derivative. So this is also a first order. All right, and then we have one other way that we classify our differential equations, and that is whether they are linear or not. Okay, so our third way of classifying differential equations is whether they're linear or not. Okay, so an nth order ordinary differential equation, so this is for ODEs, is said to be linear if it can be written in the following form. Okay, and I've written this form 2 different ways, kind of just depending on how you're comfortable with the different ways of expressing the derivatives. Basically, you're looking for the nth derivative of y, the n-1 derivative, the n-2 derivative. You're going to work all the way down to the third derivative plus the second derivative plus the first derivative plus the 0 derivative. So the 0 derivative is just the function y itself, is equal to all the things that don't have y in it. Okay, and so you can either use this dy dx notation, or you can use this y prime, y double prime. Remember, once you get past about y triple prime, we start writing this as like the 4th derivative. We put that instead of using 4 tick marks, because after a while it gets really hard to write all those tick marks, we just put the number of the derivative in parentheses there. Okay, so either one of these, but basically what you're looking for is just to have each one of those derivatives expressed out. And you can certainly skip ones. Some of them could be not included in there, but this is the form you're looking for. So let's go through these and talk about which ones are linear and which are not. So this has a y double prime and a y prime. And although this has all of the derivatives on the one side is equal to the things without the derivatives, I could certainly just subtract this term over. So this is going to be linear, right? I could rewrite this as y double prime minus sine x y prime is equal to 0, which certainly fits this form. So this is linear. On this one, I have the piece with the y prime. I have a piece with a y, so that looks like this, and this is equal to a piece that doesn't have anything with y in it. So this is linear. Okay, on this one, I have a y prime here. There's a little bit of an issue because that y prime is raised to the 4th power. Okay, we don't see that happening here. We just have a y prime all on its own. Maybe it's being multiplied by something, but it's certainly not raised to a power. So this is going to be nonlinear. And then on this one, I see a y triple prime, and it's not raised to a power, so that's a good thing. But here, my y is stuck inside of a sine function. And if I look at the way this is written here, that y has to be on its own. It can't be stuck inside of a function. Okay, just like it can't be raised to a power. So this one here, this is a problem with this sine y. So this is also a non-linear ODE over here. Okay, so these first two are linear, these last two are non-linear.